So welcome to this class. Today we will be learning about Eulerian graphs and certain properties of Eulerian graphs. So a path in a graph is said to be an Eulerian path if it traverses each edge in the graph only once. And a circuit in a graph is said to be an Eulerian circuit if it traverses each edge only once. So basically for Eulerian, no edge is repeated, be it a circuit or a path. A graph which contains an Eulerian circuit is called an Eulerian graph. So you can see that this is an Eulerian graph here, and this is also an Eulerian graph. I will show you the path. You have V1, V2, V3, V4, then you have V5, V6, and then you come to V7, V8, V9, then you have V10, after V8 you have V11, then V7, V5, V12, V2, V10 and V1. So no edge is repeated here. The vertices may be repeated but no edge is repeated. A necessary and sufficient condition for a connected graph G to be Eulerian is that all its vertices are of even degree. So this is a proof and we will be proving this. So let G be Eulerian. So G has a closed walk which includes all its edges, an Eulerian walk. Since G is Eulerian, G has a closed circuit which contains all the edges of G. And in this circuit, we find that every time we encounter a vertex V, it goes through two edges, one entering V and the other exiting V. So this happens for all the vertices of the circuit. So each vertex is of even degree because as an edge enters, it also comes out. So we have proved one part of the proof, that is, in an Eulerian graph, all the vertices are of even degree. Conversely, supposing all vertices of G are of even degree, let V1 be any vertex of G. So we have to prove that G is Eulerian. So we construct a circuit starting from V1 and going through all the edges of the graph. Since each vertex is of even degree, we exit from V1 and enter V1 through different edges. Now if this circuit does not include all the edges of G, then remove from G this circuit and let G' be the graph obtained from G by removing the circuit. So we have a new graph G' which is G minus this circuit. Since G is connected, G and G' will have at least one vertex in common, which is say U. We now construct a new circuit in G' which starts from U and terminates in U. Again, this is possible since all vertices of G' are even. And we now combine this new circuit with the previous circuit which begins and ends with V1. If this circuit contains all the edges of G, then G is Eulerian. If not, keep repeating this process until we get an Eulerian circuit. What is a process? We remove both the circuits and find a common vertex and then again find a circuit from that vertex until we get an Eulerian graph. Hence, G is Eulerian. So we have proved that if every vertex is of even degree, then G is Eulerian. Now an open walk which covers all the edges of a graph without retracing any edge is called a unicursal line or open Euler line. And a graph that has a unicursal line is called an open Euler graph. So what is a unicursal line? An open walk which does not retrace any edge. Now let G be a connected graph with 2k odd vertices, then there exists k edge disjoint unicursal lines which cover all the edges of G. So this is actually a theorem. If you have 2k odd vertices, you have k edge disjoint unicursal lines, that is Euler walks. Now coming to a simple question, is the complete graph K5 Eulerian? Each vertex in K5 is of degree 4, that is n minus 1, because K5 has 5 vertices, which is even. So K5 is Eulerian because we saw that a necessary and sufficient condition for a graph to be Eulerian is that degree of every vertex be even. Is the complete graph K23 Eulerian? So this is K23 and each vertex in K23 is not of even degree. As you can see that here you have two vertices of degree 3. So it is not Eulerian because the necessary and sufficient condition is not satisfied. Is the octahedron Eulerian? Each vertex is an octahedron. In an octahedron is of degree 4, which is even. So It is Eulerian, because if every vertex is of degree even, it is Eulerian. Is the Peterson graph Eulerian? So this is a Peterson graph, and each vertex in the Peterson graph is of degree 3. So by our theorem that for a graph to be Eulerian, a necessary and sufficient condition is that every vertex should be even, but this is not satisfied. Hence the Peterson graph is not Eulerian. So we have learnt briefly about Eulerian graphs, a necessary and sufficient condition for a graph to be Eulerian, and seen a few problems based on that. Thank you.